Yeah, hi. Welcome to Numpy 3. Um, so today's in this video's agenda will be all of this. So we'll be looking at sorting in Numpy. So basically, you can sort the arrays vertically, horizontally, specifying the axis. You can do it in place, or you can even create a copy. Then then we'll be looking at something called vectorization. This is a wrapper and not necessarily true vectorization. This is think of it as an alternative for loops. Then we'll be looking at array extensions. So basically, if you want to add a border around your matrix with a set of numbers, you can do that using these extensions. You have an np.pad and np.tile. Then we'll be looking at broadcasting. So broadcasting is basically when NumPy wants to operate with two matrices, suppose, and one of them is not the same shape as the other, then NumPy tries its best to adjust both the matrices in a way that it can perform these arithmetic operations. Then we'll be looking at element-wise multiplication. This is part of matrix arithmetic, but there is a difference between element-wise multiplication and matrix multiplication. We'll be looking at the differences in this lecture. So let's begin. So the first topic is sorting. So like I said, we have in place and we have a way to copy the array without changing the original one. So we'll look at the second one first. Just copy. Let's create our usual array np dot range 9. Now if we print this array is already sorted, so we want to scramble this array. So we can do something like np.random.permutation. So we have a random shuffled array. So now if we use the np.sort method, let's call it array2, and we pass the array, let's print the array. So we see the array2 got sorted. Let's print the first one as well. So the first array is the scrambled one, the second the sorted, and we got the sorted array using this one. And if we print the original array, it still remains intact. So we did not mess with the original array. Now if we want to manipulate the original array directly, what we can do is we can do array dot sort, call the sort method directly, and then print the original array. We see the original array got sorted. So this is in place sorting, but before that, let's look at the 2D array as well. Let's take the same thing and reshape it to 3, 3. So we have a randomized 2D array. Now if we do the same, we can do the same. We do array2 equal to np dot sort. So if you see the, okay, one sec. So if you see the original array is 582, the array got sorted horizontally. So all elements within the array got sorted. Within the sub-array got sorted. So if you see, this is 014014, that's already sorted. If you see 376 became 367. Let's look at the documentation, why it sorts that way, and because the default access is -1. So what this is it's pretty similar to sorting access equal to 1. If we specify the access, suppose do array2 is np dot sort array, and we pass the access as 1, and then we print array2, you see the result remains the same. It is sorting the elements horizontally. If we pass the access as 0, you will see, okay, the array is getting randomized again and again, but that's fine. So you see here the original array is 704316258. If you see the vertical axis, it is 732, that became 237. The vertical axis 015, that's already sorted. The vertical axis is 468, the elements, it is also already sorted. So it sorts the things vertically. Let's run it once again. 268 is already sorted. 018 already sorted. So you see 672 became 267, 351 became 135, 048 is already sorted. So that is basically how sorting works in Numpy. I'm missing something. We have checked in place as well, so you can just call array2 dot sort, or rather array dot sort, and then print the array. The original array got modified, so that is in place. Now let's look at vectorization. So basically the vectorization is simply a different way of looping or performing operations without using a loop. What it does is it acts on all the elements of the array simultaneously, and it's not necessarily faster, it's just a different way. It's a syntactic sugar, you can think of it that way. True vectorization, so there are three things that we should remember. There's true vectorization, then there is like pure Python loops, and then there is the vectorization wrapper. So if we look at true vectorization is the one we saw in the first lecture in Numpy 1. So let's take the array, which is, suppose we have an array np dot a range, let's take 10,000 elements, and suppose we want to square this array, right? We want to square each element in the array. So true vectorization is basically this. So we can just do array squared, and if we run this, if we time this, You see, it took 4.56 microseconds. Okay, let's run it once again. I think it should be slightly faster. Okay, it is the same, 4.56 micros. It is mu s, so it's microseconds. If we look at pure Python loops, let's say for x in array, or rather let's just say x square. So pure Python loops took around 875 microseconds. You see, this is 4 microseconds and this is 875 microseconds. Significantly slower than true vectorization. Now, if you look at this wrapper, it is actually the slowest. So let's take the same kind of loop again, and in wrapper, what you have to do is you have to pass in the element which is of the type that is present in the original list, which is this one. So if we take the same thing, this is a list of ints, right? If we print the array here, it's a list of ints. So we have to pass the element which is of the type that is present in the original list, which is this one. So, and then we set let's call it my operation. So we want to square each element. So within this function, we pass the element of the list, and that handles the squaring part. So we have to return this, and we create an anonymous function called vecfunc, which is basically the syntax is np.vectorize, and then we pass the function that we created. Now let's look at the Python documentation for this. So you see here, it accepts the first argument is py function. We'll not be looking at the other stuff, but the first argument is a Python function. So that is why we passed this my operation function that we created here. If you see it returns an object that acts like a Python function but takes array as input. So it takes the array as input. So what this function does is we call it like this, and then we pass our original array. So the input is this array, and since this vectorized function has our my operation function, each element of this array is passed to this function and the operation is performed. So if we call this now new array, you will see that the new array will have the squared operation. So 0 square is 0, 1 square is 1, 2 square is 4, so on. So that's how vectorization works. Now if we time this function, let's see how long it takes. So we are essentially performing the same operation in all these three scenarios. So let's see. As you can see, it's 1.59 milliseconds ms, not microseconds, significantly slower. So this is the slowest of all these three types. It's just a convenient syntax, you can say, that we can perform. It's just a different syntax. I wouldn't even call it convenient syntax. It's just a different type of syntax. So yeah, there is so you can actually do you can actually pass multiple parameters. So in that sense, you can call it convenient. So you can do something like a to the power of b. So you can pass in two different parameters, and you can create separate different arrays as well. So the ranges, the shape of the arrays have to be the same. So if one of them has 10,000 elements, the other other array should also have 10,000 elements. And this is the function, and then we pass array 1 and array 2 into our vectorized function. Int too large to convert to C long. So it just became too much. So let's do an addition instead of experimentation. So as you can see, 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4, and so on. So that's how vectorization works. Yeah, that's all there is to vectorization for now. CT vectorization. Now let's look at array extensions. So basically, array extensions, the idea is to, as the name suggests, you want to extend the array, you want to scale the array in different dimensions. So we have two methods, which is np.pad and np.tile. So what np.pad does is it adds a border of values around a matrix. So let's take a simple example. Let's take 4 elements and then reshape it to 2 cross 2. So we have a 2 cross 2 matrix. Okay. Before that, let me just explain a small. So I'll just explain naming convention. When I call it a matrix or a vector or a scalar or a tensor, something like that, what you should know is a 1D. So a scalar is just a number. You can say it's a value. A value or number is a scalar. A 1D array is a vector. A 2D array is a matrix. Sometimes we do call it a 3D matrix or a 4D matrix, but when if I'm not specifying the name, then when I call it a matrix, it's basically 2D array. And a 3D or greater array is called a tensor. So this is the naming convention that I'll be using in these lectures. So unless I'm specifying the dimensions explicitly, if I'm just saying a matrix, it means a 2D array. If I'm calling it a vector, it's a 1D array. If it's a scalar, it's a number. And if it's if I'm saying it's a tensor, then it's probably a 3D or more. Although I don't think in these lectures I'll be crossing more than 3D, but that's just something you should remember. Okay, so coming back to array extensions, so we have we have our 2x2 matrix. So if the syntax for padding is np.pad, and suppose I want to add a border of zeros around this matrix, so we can do so. So let's check the documentation first. So np.pad, the arguments are, it takes in the array, it has an argument called pad width, which is basically how many walls of numbers do you want to add around this matrix. And then mode is constant. So constant is, it takes constant, it sets the same values around all the borders. So if you have the default value it pads with is 0, so it adds a border of zeros around all four corners. And then the quarks are, you can add several other you can set you can actually customize this border by you can either add two walls around the right side, or you can add 3 on the left side. Maybe you want 5 at the bottom, or just 1 at the top. So you can customize. You can even customize the value. The default is 0, but you can set any value as the border. So let's take the simplest example. So np.pad, it's passing our value, which is our array, the array. Then let's set pad width as 1. It's a wall of zeros of it's just one wall of zeros, and the mode is constant. So the mode is constant by default. So let's see what this gives. So this is our original array 0, 1, 2, 3, and as you can see, it added a wall of zeros around on all 4 sides. Now we can change there are different modes. If you see the documentation, there is constant mode, there is edge mode. Let's see what edge does. So you see, it's taking the rightmost value or the edgemost value and pads the wall with that number. So the value here is 1, so it padded with 1. The value is 0, so it padded with 0. The value is 2, so it padded with 2, and the same thing goes on. You can check all of these different types based on your requirement using checking the documentation. But we'll be looking at some other things. So let's try. We'll mostly be looking at constant, and let's try two walls. So if you see, there are like now 2 walls of zeros around this matrix, and again you can set as many as you want. So let's say 7, create 7 walls of zeros. Now if I want to set my own custom number, so I don't want 0, I want a wall of say 8s. For that, let's see once stat length, constant value, the parameter is constant value, and you give a constant value of 8. So if you set 8, so then it fills, you'll have a wall of 8s. There is now if I want to adjust the width of on each side, so the pad width basically follows something like, pad width is basically top, bottom, it's a tuple, it takes in a tuple of top, bottom, and then left, right. So let's say I want 3 walls at the top and maybe 1 at the bottom, and then I want 5 on the right and 2 on the left, let's say. So where is our original array? So our original array is, if you see, it is let's print the original one. The original is 0, 1, 2, 3. Where is 0, 1, 2, 3? Here is 0, 1, 2, 3. Let's keep it as all zeros, I think, for now. I think that will be clearer. So you see, 0, 1, 2, 3 is here. We padded 1, 2, 3, 4, 5. 5 on the left. Right? So left is 5. 2 on the right. 3 at the top. 1, 2, 3, and 1 at the bottom. So that's how you can give custom so custom walls around on all 4 corners. And if I want to now say I want to give different values on all on these 4 walls, you can say the syntax is the same. So you have top, bottom. You can give, say I want 8s on the top and I want 3s at the bottom, and I want, say, 10s on the left and 21s on the right. So let's see how this gives. So as you can see, 0, 1, 2, 3, we have 10s on our left. This is the left. 21s on the right. We have 8s on the top and 3s at the bottom. So that is so that's basically how you add padding. Let's look at tile. So what tile does is it repeats this array along a particular axis. So it repeats the entire array, not just any one value. That is called np.repeat. That's different. So there's a difference between np.tile and np.repeat. Let's look at np.tile first. So let's take the same example. So we have our matrix. Let's look at the documentation. So if you see, construct an array by repeating A, which is the array, the number of times given by the repetitions. So the repetition. So I want this 2 cross 2 matrix to be repeated n number of times. So we can set something like, so let's say we pass the array and I want this array to be repeated 3 times. So you see, 0, 1, 2, 3 got the same set got repeated 3 times. 0, 1, 2, 3, 0, 1, 2, 3 and 0, 1, 2, 3. If I set it 8 times or 9 times, the same pattern repeats that n number of times. Now we should not be confused, this should not be confused with np.repeat. This is different. Repeat each element of an array after themselves. So what repeat does is it takes 0 and it repeats 0. It takes 1 and then repeats 1 next to in contiguous in a contiguous fashion. So you can just take the same example. This even squashes the 2D array to 1D array. So if we set the array and we set it, like say 4 times. So you see the 2D array that we have here got squashed to 1D and it's repeating the elements 4 times because that's the number of repetitions we give. This works with uh, again, we can set 9 elements, and we can do a 3 cross 3, and if we do the tile, the same operation occurs. So you see the 0, 1, 2, 3, 4, 5, 6, 7, 8, again 0, 1, 2, 3, 4, 5, 6, 7, 8. That got repeated 9 times. So that is basically the difference between tiling and repeat, and that's basically all there is to array extensions. We can use this in image manipulation, like maybe you want to change the RGB values, or maybe you want to extend the image a little bit. Again, all machine learning applications will see this in the future. Let's switch to broadcasting. So broadcasting, the idea is, it is the implicit and automatic extension of an array. So suppose we have 2 arrays, and one of them is 2D and one of them is 1D, or maybe one of them is 2D of 3 cross 3 and other is 2D of 2 cross 2. How Numpy does is, it automatically converts the smaller array to match the bigger array automatically, without our intervention, to the best of its ability. Of course, it doesn't mean it always converts all smaller arrays to match the bigger array. There are particular rules of broadcasting. So we'll look at the rules. So suppose you have a 2D, let's say A is 2D array and B is 2D, both same shape. The broadcasting works. If suppose we have A is 2D and B is 1D, it works provided they have same elements. Then if suppose A is 2D and B is a scalar, meaning a number, the operation works, arithmetic operations work. And if A is a 1D and B is also 1D, this still works provided same number of elements in shape. So let's look at these scenarios. When it doesn't work is if suppose A is 2D and B is also 2D, and they don't have same shape, does not work. Let's look at the first scenario. Let's say, let's take this one, np.a range array 1, then array 2, and let's keep them as same shape for now. So let's print array 1 and array 2. So we have 2 3 cross 3 matrices, right? So if we do an addition, it works properly. Let's take a different scenario, which is the second scenario. So A is 2D and B is 1D. So basically, let's keep it to 9. So we have 3 cross 3 and one of them has 9 elements. So the condition is it should have the same number of elements in the shape. So this has 3 elements, but this has 9 elements, so this operation does not work. This will cause an issue. So this should have 3 elements, then it performs the operation properly. So you have 0, 1, 2, 3, and it added. If you print the array, what this does is 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4, then you have 3 plus 0 is 3, 4 plus 1 is 5, 5 plus 2 is 7. So it adds each of this 1D array to each of those rows. Let's take the third scenario. With a number. So array 2 is basically, let's call it 40, or let's keep it 10 for now, just for simplicity's sake. Int object has no attribute shape. Okay. So you see, it added the scalar value to each of these elements. So 10 plus 0 is 10, 10 plus 1 is 11, 10 plus 6 is 16, so on. Let's take the fourth scenario. So A is 1D and B is also 1D. So it has 9 elements, each of them, and if we print the element, so 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6, 4 plus 4 8, 5 plus 5 10, and so on. Now let's look at the final scenario, which is both are 2D but have different shapes. So let's say this is 3 cross 3 and let's keep 6 elements. This will be 2 cross 2. So we have 3 cross 3 and 3 cross 2. This will not work. This throws an error. Operands could not be broadcasted together with shapes. So both of them have to be of the same shape. Only then it works. So that is broadcasting. Actually, there are some more edge cases and tricky scenarios. We'll look at those in a different session when we are solving some tricky questions on broadcasting. But for now, this is all you have to remember about broadcasting. Let's look at element-wise multiplication. This follows pretty much similar rules that we have discussed in broadcasting. It's the conditions are the same. If the matrices have same shape, then the multiplication works. If it's a 2D and a scalar, it still works. But if it's a 2D and any other shape, it doesn't work. Let's take the same example that we have here. Do a multiplication. It did a multiply, so 0 times 0 is 0, 0, 0, 1, 1 is 1, 2, 2 is 4, 3, 3 is 9, 4, 4, 16. You get the idea. So we can do an array times 7, which is a scalar. That also works. And if we do it's a 2D and a 1D with you see the same elements, even with the same elements, it still doesn't work. So that is one particular scenario where matrix multiplication arithmetic operations fail. Now the thing to understand is this is different from matrix multiplication. Element-wise multiplication in matrices is different from matrix multiplication. This is used for scaling purposes. So something while matrix multiplication is used in machine learning operations and linear algebra, etc. So this matrix multiplication is, you first do a column, row times column, and then you add those values to get the final matrix. So the syntax is, or rather the procedure is something like, if you have an A cross B times B cross C, then the result would be an A cross C, which means if you have a 3 cross 4 matrix and you do a matrix multiplication with 4 cross, or rather 4 cross 3, the result would be a 3 cross 3. Let's look at the, okay, let me speak about the theory first. How this actually works in theory. Say suppose you have a 3 cross 2 matrix, 1 2 3 4 5 6, and you have another matrix 2 cross 3. The way matrix operations work is, you take the row elements and then you multiply with each of the column elements with this row. So the result would be something like 1 times 1 plus, which is 1 times 1, then 2 times 4, that's the first element, then 1 times 2 plus 2 times 5, then 1 times 3 plus 2 times 6. That gives us the first row. Then you do the same with the second row and each of these columns. So you have 3 times 1 plus 4 times 4, then 3 times 2 plus 4 times 5, then 3 times 3 plus 4 times 6. Then you do the same with the third row, 5 times 1 plus 6 times 4, 5 times 2 plus 6 times 5, then 5 times 3 plus 6 times 6. So if we calculate the result, you have 1 times 1, 4 2 is 8, plus 1 9, then 2 1's 2 plus 5 2 is 10, 12, then 6 2 is 12 plus 3 is 15, then you have 16 plus 3, 19, 20 plus 6, 26, then 24 plus 9, 24 plus 9, 33, then you have 6 4 is 24 plus 5, 29, then 5 6 are 30 plus 10, 40, then you have 36 plus 15, 36 plus 15, 36, 46, 51. So this is the final matrix, which is a 3 cross 3, right? So you see the columns, yeah, okay, I forgot the most important one. For a matrix multiplication to work, the columns in the first, number of elements in the columns should be same as number of elements in the row of the second matrix. So this has to match. So if you have a 3 cross 4, and it should be a 4 cross something. So it should be the columns, number of columns should be the same as number of rows in the second matrix. Only then the matrix multiplication is valid. So let's take this same example in code. You have 6 elements, we reshape it to 3 rows, 2 columns. So yeah, the first one is 3 rows, 2 columns, and the second one is 2 rows and 3 columns. Let's print both of them. So you see it's the same scenario we have here. Fortunately, we don't have to do this tedious process in NumPy. We have specialized functions, which is something like np.dot. You can use, there is also another one, np.matmul. And there is a special symbol as well, which you can use, which is something like array1 at symbol, array2. All these perform the same operations. So let's take np.dot array1, array2. Wait, let's do a matmul. For some reason, this is 3, 4, 5, 0, 1, 2, 3. Is it? Oh, okay. It's our example is not 0, 1, 2, 3. It's 1, 2, 3, 4, 5, 6. So let's take 1, 2, 7. And so now the array is matched, so it's 1, 2, 3, 4, 5, 6. So if you see, the result is exactly the same. So 9, 12, 15, 19, 26, 33, and then 29, 40, 51. So we do the same with dot. We get the same result. We can do, you can use the special symbol as well. The operator would be at. We still get the same. So that is, so that's all there is to matrix multiplication, and that is it for NumPy 3. We'll see you in the next one.